the GNU name system.
Okay, well, yeah, I have the ticker. Well, thank you for inviting me, and also want to specifically thank David. He gave about half of his material that he gave is great background for what I'm going to talk about. So I hope you understood most of it. That's going to make my part much easier. So to give some background, just like David said, this whole thing comes a bit more of 2000s, where peer-to-peer was in vogue, and we decided that this internet wasn't decentralized enough. And then a couple of years later, people felt that this was also a bit too surveilled, and well, we had always tried to build in more encryption and more privacy. And so this GNU name system comes out of the GNUnet project, where we have built things like distributed hash tables that you just heard about, and gossip protocols and flooding protocols, and all of these things that he's mentioned are in there, and part of it is being used by the GNU name system. Now, in GNUnet overall, we're building a couple of other things. So if you're worried about the internet having been broken in Europe yesterday, you know, there might be anonymous publishing for you in there. You know, we do IPv4, IPv6 protocol translation in case this hasn't been solved yet. You know, and GNU name system, I have to apologize to Martin. I'm not mentioning reclaim ID on this slide yet. So we also have identity management on top of the GNU name system, which again relates to the next talk I hear. So lots of other things in there, but today I'm going to focus on the GNU name system for you. So our motivation is basically, well, when you build a new internet, DNS isn't exactly what you want to start with for naming. We have these problems with traffic amplification, with censorship, with mass surveillance, cyber war, you know, and we didn't want to go for the band-aid solutions, you know, DNS over TLS or something like that. So GNU name system, first thing is we said we want to decentralize, so no more hierarchy. So this is a big disappointment for some of you. The names are not necessarily global. That doesn't mean we can't have a consensus of basically saying, okay, Stefan gets to run .fr for us, you know, that's okay. We just have to put into our configuration his key, and then he can control .fr. But in principle, anybody can, you know, run their own root zone. So you can think of this as the extreme version of hyperlocal, so hyperlocal, where you have your root zone on your machine, but you can, of course, delegate .fr to Stefan. And yeah, you're very welcome, Stefan. I think you're doing a good job on that one. We can still have globally unique identification. So if you put in a public key as a name, well, that's still a globally unique identifier. So we distinguish between identifiers, which are things we can't remember, and names, like, you know, I can remember ethnic.fr. I can't remember Stefan's GPG key. Too complex. That's an identifier. The biggest difference to DNS is we have query and response privacy. So as you'll see, when you ask a question to the GNU name system, the infrastructure, even the server that stores the answer, doesn't know what the answer is or what the question is. It's encrypted. They can't see it. They can just say, well, this is the answer, encrypted, to your question. I don't know what you asked for. I don't know what the answer is, but here's what you wanted to have, and then you can decrypt it. Right? So it's much better than TLS. If you do TLS, in the DNS context, the server at Cloudflare can still see what your question is. It can still know what the answer is. In our case, it can't. Right? But it can verify that this is the correct answer to your question. Now you might say, how is that possible? Well, we'll get to that. So the result is we get also a public key infrastructure. It's all signed, so DNSSEC ++, so to speak. And we can use this for identity management. And best of all, it's interoperable with DNS. We have a proxy, DNS to GNS, runs on port 53. You can send it DNS queries, you get DNS answers back, but internally, it may use the GNU name system for top-level domains that are configured to use GNS. Should mention this is a joint work with Martin Schanzenbach, so other parties to be blamed are in the room. Don't just beat me up. Matthias Wachs and Patrick Gerber, who couldn't be here. Now, I've always been told if you want to get anything out there, you have to make sure it's usable. So I'm going to start with the user experience side. So here's zone management. Basically, we have a graphical user interface. You can also do this with command line if you prefer, where you can enter records. So for example, here I'm creating a new zone. I called it RMS for fun. And then when I created a new zone, you see here now there's a public key for that zone. Now I'm going to go here, type in a name like GNU. Give it a record type, so we have supported some of the canonical ones from DNS in our user interface, and then some new ones for the GNU name system. Now I can type in, you know, the usual information, I can type in an expiration, right? Can add TLSA records. For that, for example, I can go and type in here the domain name and click connect. Then it will do a TLS handshake and obtain the TLSA record automatically for me. So somewhat easier than what I'm used to with most DNS software. And then I have, for example, here the A record and the TLSA record for WW in the zone. What then happens is basically I have my zone, you know, or Bob has his zone here, right? And once he's done this, he can reach his zone under www.bob, or in this case, www.rms. I have my public key. I need to introduce myself to other people if I want to have a secure channel. So maybe I go to Stefan, who is running .fr. I'm going to tell him, hey, this is my public key. Please put that into the zone file. Delegate this domain to me. So he would put, well, he's now Alice. Sorry, Stefan. He would put, you know, my name into his zone file with my public key. So that's the equivalent of the NS record in DNS, right? So in DNS, he would put the IP, well, the host name and then the IP address of the authority. In our case, he would just put the public key, right? So a bit simpler. You don't have to teach people about glue problems, you know, much less work for Stefan. He just puts a public key. He only has to put one record. And once he's done that, the delegation works, and, you know, alice.bob.ww would delegate to my website. So how does the name resolution work? Well, again, we have the two parties here. Bob has his zone, Alice has her zone, and Bob will periodically put the information from his zone into a distributed hash table. If you remember what that was from David, right? Key value store. In our case, we use a 256-bit space, not 160-bit space, but that's okay. Underlying, it's a variant of Kademlia, so he'll be also happy with that. Right? It's a variant because we do some randomization to get around a couple of the Eclipse attacks a bit, but it's close, right? And we have the logarithmic performance, logarithmic connections, all of that is there. So no worries here, Stefan. And so we put this information into the DHT, and when Alice wants to figure out who is www.bob.alice, well, she'll first find out, well, who is Alice? Who's Alice? She wants to know. Well, she knows she's Alice. She knows Alice is in her GNS system. It's not DNS. So she goes and finds in her database Bob's public key. Then she goes into the DHT. So you can think of it as a local cache. Goes into the DHT and says, well, I don't know what this, you know, WW under Bob's public key is, and gets back the answer from the distributed hash table. To make this practical, here's how you can do it. Here's the Mozilla Firefox. You go into your preferences, set network settings, set a proxy for SOCKS proxy. Make sure you proxy DNS when using the SOCKS, otherwise it kind of doesn't work. And voila, you can do www.rms or something like this and resolve the names. And you can see here it's verified by GNU. Right? No longer let's encrypt there because the man-in-the-middle TLS proxy has basically verified the certificate of the website against the TLSA record. Right? Finally, TLSA is working for everybody. You know, and but then synthesized a new certificate against the web browser saying, yeah, you trust me as your proxy, and I have verified, so now it's being verified by the GNU name system for you. Right, so this is actually working. I should mention this whole manual configuration Martin has made obsolete by having a little plugin in the browser where you can kind of say just configure it, enable it, and it should be way more automatic in case this was too difficult. Okay, now we have a little privacy issue, of course, and security issue. If I just say, okay, I'm going to put this information to the DHT, everybody goes and says, well, okay, now how can I trust this DHT? Basically, instead of being able to have any DNS operator modify the answers and monitor my traffic, now I have a billion peers in the DHT that can do the whole thing. It doesn't really sound like a security gain here. So I'm sorry, we have to get to crypto. I'm going to try to do it slowly here. So in crypto, we're using elliptic curves. So for an elliptic curve, we have something called a generator. We have the size of the group, right? So that's some number n. It's usually a prime, should be a prime number. And then we have a private key. That's just some scalar modulo n. And then the public key is basically we have on the curve, we have an operation to add points to themselves. And if I add g x time to itself, I get another point. So point addition gives me a point. That's group operation. And so the point P is defined as adding g x times to itself. And that's then the corresponding public key to the private key x. And basically the security assumption of the elliptic curves is that it should be very hard to get x from P. You know, G is public, everybody knows G, everybody knows N, everybody knows lots of other group parameters, but as long as you don't know X, you can't kind of do P divided by G. That's the hardness assumption. You can't do, okay, can't do this efficiently, I should say. Yeah, well, you know, 2 to the 128 operations, and yeah, fine, and don't do it. So this is just really, this is nothing GNS specific. This is just, you know, any usual elliptic curve cryptography that hopefully you're somewhat familiar with. If you're not, you know, just trust me that this works. And it works pretty fast, 100,000 CPU cycles for the point multiplication. It's not crazy inefficient. Okay, so now for the DNS side, if you're thinking DNS terminology, well, we have labels, right? So these 63-bit things between the dots in DNS. Now, I'm going to interpret those as a number modulo n. So if you say, well, but www isn't a number, well, hash it modulo n and you have a number. Right? So that's what we call a label. And then in the end, we still want to publish records. And we basically said we're going to do DNS compatibility by saying if the record type is below 65,536, it's a DNS record type. And we're going to have a 4-bit field, so if it's above that, it's a GNS-specific record type. So the DNS people can continue allocating record types, and there won't be any conflict with ours. But so we have record set of records. So this is, you know, IP addresses, TLSA label records, whatever else we want to publish in there. And this is just in the clear text, in the zone under the public key P for the label L. So every zone, we no longer identify as a domain name. We identify the zone as a public key. So the public key tells us which zone it is. Every zone must have a public key, just like in DNS, every zone must have a SOA record. Okay, so these are the in clear text records in the zone P under label L. Okay, now when we want to go out there and ask the DHT for information, well, the DHT looks up things by a hash. All right, so we're going to call the hash that we're going to send out for the DHT to query for records, the query hash, so Q, for the public key P under label L. I'm not telling you how you could get this yet. I'm just telling you this is what we're going to send out to the network, right, to get this information. And what we're going to store in the network in encrypted form is what we call a block of information. DNS has these strange 512-byte limitations. In our case, we said, okay, 64 kilobyte is the max. You know, it seemed a reasonably sufficient number, but maybe in 20 years they're going to tell us, why did you only pick 64 kilobytes? But it's not supposed to be for publishing files. It's supposed to be publishing metadata, right? So we have the encrypted information for label L in zone P that we're going to publish under QPL. That we're going to call, so this encrypted thing is we're going to call BPL, right? So that's what everybody can have. It's just encrypted. You shouldn't give any information from that. Okay, that's the terminology, just so you know what the various things mean. Okay, so how are we going to do this? If I want to publish the records, you know, I know them in the clear text as RPL, right? I'm going to first do the hash of the label and the public key. Right? So take the label and the public key, hash those two together. Call that small h. That's a number. And then I'm going to multiply that number with the private key of my zone. Remember, x was the private key of my zone. So multiplying two numbers gives me a number mod n. And that turns out to be another private key. Right? D is still a private key. So I can derive one private key from another private key. Now notice, D is literally any private key. If you don't know what H is, and if you don't know what L and P is, you don't know what H is, you know, you have no relationship. There's no clear relationship. If you want to get D, you need to know X and you need to know H. Right? So D is just as secret as X was. Okay? So now I'm going to do is I'm going to take my records and I'm going to encrypt them with symmetric encryption using an encryption key that I've derived using a hashed key derivation function, so fancy hash function, also from the label and the public key. So if somebody doesn't know the label and the public key, somebody is not able to do, you know, enumerate the zone, somebody doesn't know the zone public key or doesn't know the label, either one of the two can serve as a secret, they can't decrypt this. Agreed? Right? Symmetric encryption is a key if I don't know what the inputs were done. Okay, so I'm going to encrypt the records with that, and I'm going to sign it with the little d. And I'm going to attach DG, which is the public key corresponding to the signature. Right? Just like XG was the zone key, now I have DG, public key of the signature. That's the block. And I'm going to publish this under the hash of DG. What does this mean? Well, if I'm in the node, I'm a DHT node, I can check that this BPL should be published under QPL because I can check that DG hashes to, H of DG. That's a very trivial operation. And I can check that this signature matches this public key. So it's a well-formed record. Now, if you are not in possession of the X, you can't create this record. So I also know it comes from some zone. But I cannot figure out what the zone is. Again, based on the security assumption of the elliptic curve, I can't divide this DG by P. So I cannot know, what the label is or what the public key was or what H was. I can't even tell which zone this record belongs to. Right? So I have to be neutral infrastructure. The DHT can't know for whom it's publishing records. It doesn't know what it publishes. But if it returns these things, well, anybody can check. And if Stefan gives me a wrong record, I go and say, Stefan, did you not check the signature? Right? Now, there's one thing we do put in the clear text here that I'm kind of omitting here, which is there's a timeout value. I can say this thing should only be valid in the network for whatever 2 weeks, right? And then afterwards, everybody should drop it. But this timeout value is really not security sensitive. It's more, housekeeping. Now, if I want to search, I don't have the private key. But I assume, again, I know the zone's public key. Remember, .fr is in my root zone, so I have the public key of Stefan in my keyring, maybe gotten by default as my operating system, just like every good recursive resolver has gotten some trusted root zone. So I have P, and I've guessed the label is ethnic. Right? Somehow I magically knew that one. If I don't, I have no chance. If it's a password, he has to give it to me to help me have access. So I know the label, I know the public key, which means I still can compute H of L and P. So I can get my small h. And now comes the magic. Really complicated magic. I can compute H times P, right, on the hash of that, which is the same as H times X times G. What? P was XG. Very complicated math here. And then this is the same as H times DG by definition of D. Right? So I get the same query, right? H of DG is what it was published under. I can compute H of hash of HP. So I can ask this question, and of course I can check the signature myself, and I can do the decryption. If I know the public key, and if I know the label. If I don't know either of the two, I get nothing. I can check that this is the right answer. I can't decrypt it. So basically the only way to get information out of GNS is to know the zone's public key and the label. And of course, I can learn public keys over queries for other zones first. So I have query privacy, response privacy, and signatures in this system. Okay. Now, we also can have, as I said, global unique identifiers. Very simple method. You just take the public key and append it at the end. With elliptic curves, fortunately, that barely fits into a label. So we can just put a public key at the end and we have a global unique identifier, just nobody can remember it. But if you do need this in some kind of application where you go and say, I need global uniqueness, well, as long as you don't expect users to remember these things, you can just form something like alice.bob.public key and it works. We're also worried about key revocation. So for revocation, you basically sign this with your private key. This zone is no longer valid. You mentioned flooding earlier. We flood it basically over the links in the peer-to-peer network, over the DHT and other links if you have more. Now, we use Epstein efficient set reconciliation. You mentioned that earlier. For peers being offline, if somebody reconnects and has missed some floodings, we use this efficient set reconciliation to kind of get the missed revocations across. To prevent the DDoS potential, you mentioned flooding is bad for DDoS. You have to do a proof of work calculation. You mentioned that as well. Before you can revoke a key. So basically, if somebody just goes, oh, make a public private key pair, revoke it, and does this 100 billion times, well, they could also just mine Bitcoin instead. And we try to basically make the cost of doing a revocation CPU-wise expensive enough that this is not effective denial of service vector. Of course, you can do the calculation ahead of time. So if you're Stefan, you're running .fr, and you go and say, if I'm compromised, I can't just say, well, I have to wait a week for computation before I can revoke. Well, just make your proof of work calculation ahead of time and only then go live with .fr, Stefan. Right? Easy to do. And yeah, of course, you can store the revocation itself offline in case you don't want to be hacked and have your zone revoked by accident. Okay, so revocation is in there. Now, I have to thank the IETF for the more recent developments. So initially, we had proposed to use .GNU as a protocol switch, right? And as Warren here observed, this is how you should do it in his RFC. But as I said, he's wrong here. You know, we asked the IETF, please reserve .GNU. And following the usual IETF way, they didn't follow their own process. And so we decided, okay, if we can't get .GNU, we're just going to take everything. So the latest implementation that we have released basically allows a user to override any domain name with the GNU name system. Just put in the public key that you want to have for any domain name, and it will go to GNS instead of DNS. So we're no longer looking for, does this end with GNU? And the very nice effect was we did then usability studies, and the users love it. They can't even tell they're not using DNS anymore, right? Now, as application developers, you may not like it so much, right? But for users, you know, it's great. And we have a DNS proxy, so as an application developer, you can also no longer tell if you're using DNS or GNS. It depends on what your network provider or your user has configured. Maybe there is privacy, right? That's a slight disadvantage. As a user, I generally like to know if I have privacy or not, but here it's now completely intransparent. On the technical side, we did demonstrate that our DHT scales to millions of records. David will not think that that's a great surprise, but you know, you have to do some tuning before you can actually show this. We implemented a GNUnet zone import to basically, given a list of .fr names, hit Stefan's servers until they give us all the information, because .fr does not allow zone transfers, so you can just brute force it if you have a list of names. Very strange that they publish the list of names but don't allow zone transfers for .fr, so you have to ask for every single one what's the DNS information. We also implemented Ascension, which is a tool that does proper zone transfers, so slightly more efficient, and used that to import .se and .bfh.ch, and made sure that basically all of the record types we find in all of these three small zones are supported by our system. Okay, so to conclude, DNS monopoly is over. GNS is simpler than DNS. No more glue, no NSEC3, no RR6 are required. We have private name resolution, censorship resistance. If Stefan blocks you, I can just put your zone in directly and I'm fine. We don't require ICANN or a root zone or IANA special use TLD. You just take everything. And if you previously saw about the GNU name system and you told people, if you see .GNU, that's special, forget about that. Now teach people about that there could be other protocols than DNS for name resolution, and they just can't tell. And if you want to get your top-level domain and you're a member of DNSOP, you know, we welcome your donations, just like ICANN welcomes your donations. It'll help us scale our infrastructure. Thank you.
All right, thank you. Are there any questions?
Yeah, David.
Yeah, can you say a little bit more about how adding a little bit of randomness thwarts the Eclipse attacks on Canoe?
Yes. So basically what we do is we first do a random walk over the peer-to-peer overlay network and then start the Kademlier, let's say, gradient descent, greedy algorithm. You can still have Sybil. You know, I'm not saying we're solving all the problems. You're solving specific Eclipse attack problems that way. You know, so Sybil attacks, if you have a very large number of Sybils, are still a theoretical issue. I don't know if we're in practice going to have that many Sybils, especially once all of the DNS operators run GNS DHT nodes on their fat DNS servers. That's my hope. But it addresses some concerns, right? So you do this random walk first, and for the random walk, you need to know kind of what the size of the network is. So we have a network size estimation algorithm to get log n of the network size, and if you do log n hops in a small word topology, you know you had a random starting point, and thereby, and if you do this every time you do a query and you do it repeatedly, you start from different starting points, and you end at different places possibly, and so a Sybil attack becomes less effective. An Eclipse attack becomes less effective.
Reminder to identify yourself at the mic. Okay.
Hi. My question is about what would be the information inside the key.
Your name? Your name, please?
Oh, sorry. Shubir. My name is Shubir Ali. Okay, so my question is, what would be the information inside the key? If the two nodes are running in the cluster, right? So the active node is got failure. So how would the second node would work with the key?
I'm not sure. Information, the key. A key is just a public key or private key, or I'm not sure what you're.
You know, actually, the machine is running. The zone is running on the machine, right?
If you're running a zone,
Yeah.
You're basically taking all of your record sets,
Yeah.
and you periodically publish them into the DHT in an encrypted form.
Okay.
Right. So even if you go offline, the DHT will cache that information for some amount of time.
Okay.
Does that help?
That's okay.
Giovanni, SIDN. So I'm also a researcher, and I'm a DNS guy, and I work for an operator, so I have to disclose that. I'm always excited about seeing new naming systems, for me, like DNS, it is nice to see new name system, but the real thing of the DNS is about high availability and high performance that it can deliver. It's not only the name system. That's very important. If you want to propose something, you need to do what you're doing. But I think your real enemy should be something that you can deliver high performance availability that DNS can deliver with any cache replication, caching, and a bunch of other stuff, and trust, and gain trust of the people.
Of course, but caching we can do in the same way. The DHT caches records, intermediate nodes can cache records, and DHTs can be high performance. And unlike DNS, we don't have problems with out-of-bailiwick, so we don't have as many redirections. In our case, caching is also implemented on the client side, right? So end-to-end side, so we can have possibly, if you have frequently used names, they might already be cached locally. So caching is still considered in the system. In fact, we have some additional features I did not mention, like when in DNS you time out a record and you go down to time to live 0. Then kind of all the caches become stale, have to drop all the records. In our case, you can already tell in the records that, hey, this record is going to be valid after a particular point in time. So I can pre-populate caches with information that will be valid in the future ahead of time, which is something DNS cannot do. So we've got some features to actually do better in caching than DNS.
Yeah.
And performance-wise, I don't see how we inherently are worse, but of course we do inherit availability and performance properties from the DHT. But DHTs aren't necessarily super slow.
So maybe a thought exercise for you folks for next, continuing this work, how would you compare if you would run .com with more than 100, if you would run .com, which has more than 100 million domain names on it, and allows for dynamic updates and delivers very fast response time. So maybe something you want to consider in the future.
Well, one of the things we have seen is in terms of importing large zones, most of the churn, we studied .se for that, is in the RR-SIG records. And so since we don't even have RR-SIG records, most of the churn of the DNS system won't even touch us. And the import cost primarily for us is doing the signatures. And well, if you have DNSSEC, the signatures you use there will be more expensive than EDDSA signatures that we use. So there, again, don't see a problem with significant updates. Of course, if you have things like dyn DNS, where you have people changing their IP address every couple of hours, that'll be harder with the DHT, I agree.
Thanks.
And one thing we also can't do is using GNS to do things like configuring DOH over DNS. So .rpar reverse lookups don't exist in our system.
Just quickly, we have to close the line after the last speaker, after the last person.
This is Ulrich Wisser from the Swedish Internet Foundation. We are, of course, happy that you used .se for your tests. And but I would know if let's say I would like to go to the IETF's website using the GNS, then if I understand you correctly, I would need the IETF's public key first.
No, if you have the public key of .org, and .org has the public key of IETF, it will still work fine.
Right? Then I have to have the public key of .org.
Right. And if .org supports GNS, we would, of course, put this into the default configurations, just like you would do with HyperDNS, and everybody tell who the .org's name servers and IP addresses are. Right. Okay. Now, if you go and say .org does not support GNS, but IETF.org does, you could put into your configuration saying IETF.org is this public key, and basically only slice out this part of the namespace for GNS and leave .org with DNS.
Okay. But that sounds...
Yeah, you start with like a host file, but that's hyper DNS, right?
That sounds awfully that you suppose that we would make another central organization to collect these public keys that you want to distribute to everybody.
We allow you to automate that process because we have this idea of curved DNS. We stole that from Dan. Basically, if you call your name server something that has a public key in our format in it, we'll just say, that's your public key. So we can kind of steal that information if you provide it.
Okay, thank you.
Wes Herdeker, ISI. 0 hats on my head at the moment. I have a lot of them that might relate, but really cool math. I mean, I think that the math behind this is really slick. And so my question is more about, especially the screenshot of the web browser showing the RMS page, for example, and the usability of how you might get there, because, yeah, that one. So if I'm understanding this right, there's sort of this new global collection where you might have a whole ton of essentially, I don't want to call them roots, they're public keys, and under which there's a whole bunch of names.
Yeah.
And you're going to collect all of these public keys on your system, and maybe there's hundreds, maybe there's thousands, maybe there's millions, maybe we each have one, which is really kind of cool.
Well, the idea is everybody should have one, but you don't need to, you can have global names, which are kind of like the consensus. We all agree that we put those into our configuration, and then there'll be local names. So maybe I put RMS into my configuration, but you don't. And then we can't use the RMS names as global names. We'd have to do whatever, www.gnu or rms.gnu.org. Right? But if I go and say, well, I like this website and it has been censored by my government, but I have its public key, I can just put that in and bypass the censorship operation.
Right? So that brings me
kind of have both. We have a
right. So I understand that. So that brings me to my question, because there is no definition of a global name. You sort of stated that actually on the first slide. Don't go back there. But
no, global names comes from global consensus. Another question is, how do you, who do you get into the global consensus?
How do you get to global consensus? So the reality is that the URL, my question is actually related to that URL, which makes it look like you have no notion there of what public key is actually serving that global name. So I mean, the reality is I would expect from a usability perspective when I type
this is not a global name. This is a local name. So I have RMS configured on my system.
Right. So as my application level, if I put in RMS, I'm going to go search through all of my public keys and look for RMS under each one. Which one do I pick? Which one do I get?
No. In the configuration, you say .rms equals public key. You locally as a user give each top-level domain name that you want to capture, assign it to a public key.
And you can have conflicts.
You can assign one public key per top-level domain. You can assign the same public key to multiple top-level domains if you so choose.
So you have to manage that list.
Well, I would assume that for the global consensus, you get a sane default, just like your network service provider gives you a sane default for the root zone.
I look forward to that consensus process.
I assume we will descend on that.
So Warren Kamari, Google, also speaking without any hats. A couple of things. First, your URL at the end, unfortunately, is incorrect. I think you need to add old.gnunet.
Yes.
Yes. Just so people want to find it.
Yeah. Thank you.
So I understand that kind of part of your design goal is to not have a centralized system, right? You end up with a consensus-based thing. Let's say that RMS ends up being a consensus global name. That's really great, and everybody who's using the GNS system can use it. What do you do when, for example, the other users of the namespace, like the DNS, end up trying to use RMS as well? You're going to end up with... We
generally would say we advise ICANN to not assign any more names.
That might...
We were told the same thing from IETF before, and so now the advice is the other way around.
Okay.
Any name they might assign from now on is likely to be a conflict with some user.
Okay, that's a perfectly fine answer.
Thank you.
I had a third point, but I don't remember what it was anymore.
Okay, that was fun. Thank you very much for bringing this to us.
You're welcome.